Hello there, I'm Thomas. This is German American pilot flying the Boeing 787-900 tonight's flight from Zurich International Airport. We're going to be able to fly in Zurich, Switzerland, Germany, then coming back to the Zurich International Airport. Runway on 1449, let's localize the landing. Surrounding the cockpit for the pre-takeoff preparation of the quality wings Boeing 787-900 and Microsoft Flight Simulator X FSX. I'm going to start showing you the cockpit instruments displays and the functions of the Boeing 787-900 jet aircraft. I'm going to start with the primary flight display that displays the airspeed indicated, the airspeed selected from the autopilot and flight director system panel, the ground speed, the radio altitude above the ground level, the barometric altitude above the sea level, the barometric pressure with inside atmosphere, the target altitude selected from the autopilot and flight director system panel, the vertical rate of climb and descent of the aircraft, the VSI, the vertical speed indicator that displays also the rate of climb and descent of the aircraft, and the trigonometric angle, the steepness of the trigonometric angles and decrease can climb and descent. You can select from the autopilot and flight director system panel. I'm going to show you also the primary flight display. Um, Contains the artificial horizon with the altitude indicator, the pitch ladder degrees, and the bank angle in degrees. Also, you can see the ILS localizer, the horizontal localizer, and the vertical glide slope for alignment and guidance to the airport where we need to land. We have the display of the ILS localizer crossbars and the horizontal and the vertical glide slope needle, so you can align the magnetic north pole heading of the runway you want to. Now we have also um, the flight director crossbars for manual guidance of the aircraft and the autopilot crossbar for automatic guidance of the aircraft. We have also the flight mode and zero with the autopilot and the auto throttle, later on vertical navigation modes. We have also the integrated display, the standby navigation display. You can see the flight plan and the magnetic heading or track. We have the magnetic north pole and true north pole, and the magnetic variation over around the world. We have the navigation display that displays the GPS position, the terrain map from the weather reflections. You can see also the terrain around you. You can see the horizontal and the vertical profile of the aircraft, the airports, the waypoints, the GPS position, the magnetic heading and track, the magnetic north pole and true north pole magnetic variation again. Depending on where we are, we have, as I told you, the airport's position, the runways we're gonna use for takeoff and for landing, also displayed in the navigation display, the taxiways we use, we have the GPS. So we have also the waypoints, the nav rates, the base stations, radios. We guide the aircraft when we fly. The waypoints that include horizontal and vertical navigation fixes that we use for the flight plan and the aircraft has to fly through from takeoff, climb, cruise, approach, and landing. I'm going to show you right now. So we complete our flight plan. For this purpose, using the flight management computer, I just input all the data of this aircraft for this flight. So we have the takeoff gross weight, that includes the empty weight plus the passenger plus the cargo on board, as the fuel on board, the left and the right wing tank, the center tank. This calculates also the center of gravity of the aircraft for this flight, and the mineral dynamic core position, the Mach of the forward wings, that is about 33% of the forward aerodynamic of the forward wings, the aerodynamic chord of the forward wings. 33% of the chord of the wings, and is the position where the maximum aerodynamic lift occurs in the wings. This calculates also the center of pressure in the top surface of the wings, and we have also the stall begins in the top surface of the wings for a given angle of attack of an airspeed and altitude of the aircraft in flight. So the aircraft wings start to stall from this position, and we can calculate also that. We have also the mean aerodynamic chord position also is used to calculate the horizontal tail trim stabilizer position for takeoff. So we're gonna trim the horizontal tail of the aircraft up and down depending on how we need. During the whole flight from takeoff, we trim up the tail like 4.35 degrees for positive nose pitch rate climb. So we have The horizontal trim stabilizer also has been calculated of the horizontal tail surface. That includes also the horizontal, the elevators of the aircraft for climb descent. So we have, I'm gonna show you also that we have also, you can see here, we can use these switches for trimming up and trimming down the horizontal tail of the aircraft over here. So this is the horizontal tail I'm talking about. So we can trim up and trim down the aircraft horizontal tail during fly to stabilize the aircraft in the fly. Also, you can see here we have the wings. The wing surface area holds the weight of the aircraft as it flies. We have the mean aerodynamic chord position, about 23% of the Mach is about here, where the maximum aerodynamic lift occurs in the top surface of the wings, and also the stall will begin. We have the thrust vectors from the engines. You can see the top surface of the wings and the bottom. I will show you the difference. The vertical tail also. So we have the longitudinal axis, the lateral axis, and the vertical axis that transverses approximately here where the mean aerodynamic chord position is, the center of gravity of the aircraft located. So you can see the bottom surface of the wings is more flat over here. So the airflow of the air mass as the aircraft accelerates using the engine thrust is moving slower below the wings, so we have higher pressure below the wings because the air is moving slower below the wings. And as the aircraft also accelerates for takeoff, you can see the top surface of the wings is more curved, it has higher curvature, so the airflow is moving much faster above the wings. So there is a lower air pressure above the wings, which sucks the aircraft up into the air. So this is the general explanations. You can see also the tails. I told you the horizontal tail here. You can see the horizontal tail for climb, descent, and the rudder we're gonna use later. So we trim the horizontal tail all the time. We move the control surfaces using the control. We'll show you the flight control surfaces here. Now, so you can see the flight control surfaces include. We have the control. This switch for the horizontal tail trim. Horizontal tail trim, and you can see also here pitch trim, nose up and nose down over here. So you can use this switch. We have also the parking brakes. So it's the horizontal tail trim stabilizer, and we have the cutoff switch, the normal L1 and R2, as you can see. So this also disconnects from the autopilot and flight director system panel the auto trim function of the horizontal tail of the aircraft. So we have a failure of the hydraulics L1 and R2 over here, the auto trim functional, because we have also automatic trim from the autopilot and the auto throttle switch. If we have a failure of the some hydraulic system, we have to disconnect, open this guarded switch and disconnect from normal to cut off, as you can see, and use only the alternate pit string. So you can see where the pit string is positioned. We disconnect, then you can use only the normal pit string for the horizontal tail of the aircraft. And you can see the pit string position over here. So you can see the stabilizer and the rudder trim over here, 4.25 degrees, the flaps position also. So you use the rudder trim here. You have the small switch. You have the transporter. I will show you all the instruments right now. Also the overhead panel, we're gonna make an engine start demonstration. Also, you had to use the APU here, the auxiliary power unit, for starting the engines. So I think I will have to continue now with the rest of the systems. I will explain you about the navigation display, how we input the data of the aircraft, the takeoff gross weight, that includes the empty weight plus the passenger plus the cargo plus the fuel on board, the left and right wing fuel tank, the center tank. This calculates the center of gravity of the aircraft, the mean aerodynamic chord position of the forward wings, and the horizontal trim stabilizer. We use the flaps for takeoff, like 15 degrees of flaps. You can see I have extended the flaps here also. The wings are down. So I use this handle here to extend or retract flaps. So we're gonna use 15 degrees of flaps for takeoff, and we use the runway data we have stored in the flight management computer, the runway left, the runway slope, the runway conditions, if it is size, right or wet, the wind direction and speed, the barometric pressure, the barometric density of the air, and the temperature of the air. So we have the calculations about the takeoff speeds, the V1, the V2, and the V2, which is the takeoff speed after liftoff. So we have also the V2 plus 15, and we're gonna use this as airspeed for after liftoff V2 plus 15. So we're gonna have also the complete flight plan of the aircraft for this flight. So we input using we select the runway for takeoff. We have the Zurich International Airport runway 14 we're gonna use for takeoff right now. You can see the runway over here this way on this side. So we are in the Zurich International Airport, Lszh. So we're gonna use the same airport and the same runway 14 for my less localized landing also. So we select the departures, the seats, the SAD arrangement, departure waypoints and fixes that include horizontal and vertical navigation fixes with initial climb of the aircraft after takeoff, the top of climb. We have the flight plan created, so we're gonna have the aircraft is gonna cruise through some waypoints after the top of climb. Then we're gonna have the top of descent. We're gonna start descending the aircraft back into the airport and direct to the vectors for landing. So we're gonna have the aircraft. We're gonna descend it out to the start. The standard terminal arrival waypoints and fixes. We select also everything is calculated automatically using the flight management computer of the flight plan. So the stars include horizontal vertical navigation fixes for the final approach and landing of the aircraft, and also the glide slope for the approach and the airspeed. We're gonna have everything managed before we arrive to the runway. So we're gonna have also the Lszh localizer. The Lszh localizer, the instrument landing system of the aircraft in the airport. For the runway we select for landing. We can tune the Lszh localizer automatically already using the flight management computer when we are in the approach mode. So below like 3,000 feet above the runway, we're gonna capture the Lszh localizer, the glide slope, and the horizontal localizer and the vertical glide slope. We're gonna have this displayed in the primary flight display, and we're gonna align the aircraft with the magnetic north pole heading of the runway for this purpose, and also the Lszh localizer is going to be aligned with the same heading, 136 degrees magnetic north pole heading for this runway. So we're going to make an alignment for landing. We're going to see that also. I'm going to use also the Lszh localizer crossbars for this purpose, and you're gonna see the complete flight from takeoff, climb, cruise, descent, approach, and landing. You're gonna have the horizontal vertical navigation profile using the flight management computer, the flight plan, flight path or route for this flight. Also is gonna supply some data to the autopilot and flight director system panel like airspeed. We're gonna use also, if we need, the DL nav and the VNav, the lateral navigation, the vertical navigation of the aircraft that can be guided by the autopilot automatically. You're gonna see also that. for horizontal and vertical guidance. We select also in the autopilot flight director system panel. Also later the airspeed guidance of the aircraft. We select the airspeed. We have the autopilot engage and disengage switch, the auto throttle left and auto throttle right, engage and disengage switch, the flight director engage and disengage switch, the airspeed select now. We select the airspeed in nautical miles, knots or Mach speed, and this will command the engine's thrust. We have the General Electric GNX engines installed in our aircraft, and one in the left wing, one in the right wing for symmetrical thrust and redundancy, which are jet engines that provide a lot of thrust. So each one contains a gearbox with the FADEX. The FADEX are the full authority diesel electronic control computers. One installed per engine gearbox controls monitors and displays all the engine data using the upper or the lower ACAS engine indication controller system display of the Boeing 787-900 aircraft. So we have a display here, the multifunction display or ACAS engine indication controller system display. You can see the engine data. Like the N1, which is the low speed starter shaft, the low pressure compressor, and the turbine of the turbofan, which is the engine on the left and the right. The takeoff limit 100.8%. The N2, the exhaust gas temperature. The N2, which is the high speed and the high speed, high pressure starter and shaft. High pressure compressor of the turbofan, which is the fuel flow per 1,000 kilograms, 1,000 pounds, oil pressure, oil temperature, oil quantity, and the vibration of the two states of the engine. You can see also other data like gross weight, total fuel on board, the fuel temperature, other messages. We have some failure, total air temperature. We can see also here we have the pressure. We will display the outflow valves, the pressurizer from the left and right. We will select this. You will see display with messages now that we have open in the manual mode. Cabin altitude, outflow valve out. You can see the outflow valve also, the position, the cabin altitude, and the rate of climb descent of the cabin. So the FADEX controls, monitors, and displays all the data. You can see in the left and the right engine, that I told you, N1, which is the low speed, low pressure starter, low pressure compressor, turbine engine, the exhaust gas temperature per engine, the N2, which is the high speed, high pressure starter compressor of the turbofan engine, the fuel flow per hour, 1,000 kilograms, 1,000 pounds, oil pressure, oil temperature, oil quantity, and vibration of the N2 states of the engine. The pressure inside the engine, we have overpressure, under pressure. We can open and close the outflow valves to regulate the pressure inside the engine. Also, the pressurizer from the outflow valves has been admitted for other systems like the hydraulic fluid tanks. For pressurizing the hydraulic fluid we need for the flight control surface, so you know a little bit. For cabin pressurization, we can engine anti-ice, air conditioning, and ventilation, also from the bypass states of the engine, from the front fan bypass air. So we have also the as we climb and descend the aircraft into higher and lower altitudes, we have a difference of airspeed of the aircraft is flying like 2 or 3 times faster than that of the sea level. If we take off and then climb to the 30, 40, 20, 30 or 40,000 feet above the sea level. As we climb higher, also the pressure of the air is becoming half of the sea level. The temperature of the air is becoming freezing, like minus 30, minus 40, minus 50, minus 60 degrees below zero. Also, as I told you, the air pressure and density, the oxygen level all become half than that of the sea level or even lower. Also, the aircraft flies with an airspeed 2 or 3 times faster than that of the sea level, so we have a difference of air intake also from the front fans inside the engine. So this creates a different fuel air mixture request every second, so this is adjusted by the FADEX automatically every second. So the FADEX also adjusts the fuel air mixer automatically instead of doing manually like on the turboprop aircraft. So you don't need to use that auxiliary engines at aircraft, or you can anyway. So also with descent back to the sea level, we have to do the vice versa. This is done automatically again by the FADEX. Um, as I told you all these things, also the FATEX control engine starts, engine shutdown, engine failures. Also we have the APU, the auxiliary power unit. I'm gonna show you we need to start the engines in the ground, provides alternate current for an engine start, and also pressurizer. We have the pressurizer from the small air turbine in the tail of the aircraft that is used only for engine start and for a backup in flight. It's also admitted using is admitted into the engine starters during the engine start process. Then this creates a pressure inside the engines and starts the rotor of the engine start rotation before we admit the fuel for ignition. So you're gonna see also the engine start process. I'm gonna show you now the flight controls of the aircraft before showing you the autopilot and a few more systems. We're gonna make an engine start demonstration and complete flight from takeoff, climb, cruise, decimal approach and landing. So now I'll proceed with the flight controls now of the aircraft. I'm gonna show you the system we use for controlling the aircraft. So you will see here. I have to show you like this so you can see. So you can see here we have you can see the size of the aircraft. So you can see I can control the aircraft flight controls. Hope you have a good view with light on, maybe not so much light. So you can see I can control the aircraft flight controls like this. I can climb and I can descend. I can make turns to the left, turns to the right. Oh, maybe better view like this. So turning left using the ailerons and the spoilers in the left and right wing. Turning right, climb and descent. You can see how fast this is done. Climb and descent, also balancing in flight and the rudder pedals. So we have the thrust from the engines over here. Use thrust levers for actuating the engine thrust. So maybe you have a better view like this. You can see the engine thrust like this here. Moving up and down. So climb and descent. Rudder pedals left and rudder pedals right. You can see the rudder pedals are used for the vertical tail of the rudder, for nozzle steering and for braking in the ground using the toe brakes. And we have also for nozzle steering this tiller here. We can disconnect the rudder pedals so we use it together. So we have also thrust levers and the horizontal trim stabilizer over here, these small switches. So I will show you now also the outside view of using the same flight controls right now. So you will see the outside view of the aircraft, how to use the flight controls using the side stick. You can see the Logic Stream 3D, which I use for the Airbus, which we use for Boeing simulation. So you have direct input. The side stick deflection is proportional, as you can see, to the yoke deflection over here. Side stick deflection proportional to the yoke. Also the flight controls, so you can climb and descend, make turns left and make turns right, and also the rudder pedals, thrust levers. You can see both sides are moving together, they're interconnected, so they move together. So the captain and the first officer move together in flight or in the ground. So also you can see the outside view over here, the flight controls. So you can see I can extend the speed brakes, also use like this, make turns. You can see the flight controls I use. Every time, so climb and descend. So you can see the horizontal tail. and make turn to the right and make turn to the left. So this is all the flight controls that we need. You see how proportional are inside with the outside over here. So we have the flight controls like this. As you can see, so this is all the lesson for the flight controls. Now I will show you the rest of the systems. As you can see, I will show you now the overhead panel. I will make the engine start demonstration, also show you the autopilot and flight director system panel and the displays, what they display in proportion to the overhead panel. So maybe we have a few more minutes for making the flight. So I'll show you a few more systems here. You can see, as I told you, the thrust levers. You can see we have the auto throw disconnect switch. We have the thrust reverse. You extend, you open up and you extend the thrust reversers like this. We have the fuel control, the left and the right engine. So you can see the thrust reverse over here, open, deploy it like this. So this slows down the aircraft after landing. You can disconnect and reconnect again one more time. You cannot do that in flight, only after touchdown or in a braking action or executive takeoff. So we disconnect the thrust reverse. You can see we have the landing gear here, extend and retract. Some messages, the standby display, the landing gear, the lock override. Over here we have a failure of the landing gear hydraulics, alternate and lock override, the auto brake. You can use reject takeoff also. A few more systems. So we have also here the fuel control to the left and the right engine. You can turn off the engines by turning off the fuel flow. The fire extinguishers for the left and the right engine. You can open and switch, pull out and switch. That will also cut off the fuel flow. The transporter, the rudder trim, and some other radio communication panel. We have the mouse for the pad here for controlling over here the displays. The flight management computer. Also we have the autopilot flight director system panel. You can see here the auto throttle left, auto throttle right. Over here flight director on and off, autopilot disengage, LNAV maybe use LNAV and VNAV. As you can see, the heading bang angle over here. So we'll make a few changes. The heading, I'm gonna use the heading for this runway and an airspeed 253 nautical miles per hour not. So we can use also max speed if we are flying higher altitudes. Vertical speed, you can see, use descent or climb the other way, level off and climb. So we're gonna use a climb plus. You will see the altitude we select after takeoff, like 25,000 feet. This in case you need to use any of these during flight. It's the autopilot and flight director system panel. So this is the autopilot for director system panel. Also in the overhead panel I'll make the engine start demonstration, also the APU, so the electric system, the left and the right engine, IDZ, the great dry generator. We have electric power from the left and right engine. Also we have the batteries, 80 volts for the amber hours. The IDZ provides 120 200 volts alternate current, 120 200 volts, 120,000 kilovolts each left and right engine, 120,000 volts. We have the contactors, and we can disconnect if we need the IDZ, the great dry generator from the engine drive stuff. So I'll show you that. We have also the APU, the auxiliary power unit when I use for starting the engine. We have the primary flight control computers, the hydraulic system, left and right engine hydraulic pumps, the electric pumps, the fuel system, left and right end wing fuel tank and the center tank and the fuel booster pumps. The engine start, electronic engine control for the engine, some systems I will explain you now, and I will show you in the overhead panel. You see also in the display the diagram of the pressurized air from the left and right engine from the APU and the cabin pressurization. So I'm gonna start now showing you all these things. I'll show you the flight controls. So now we go for the engine start demonstration. So we're gonna start the electric. As you can see, the battery, the APU generator, the controllers for the IDZ. So we're gonna start over here. We have the primary flight control computers to the auto position. The heading reference, this is the IRS instrument inertial reference system. The flight control surfaces. You can see the whole of the cockpit and the flight controls over here. Primary flight control computers, some other systems. We have the window sheet here. We have the ram air turbine we use for a backup if we have a failure of the hydraulics. You can see the hydraulics over here next to the electric. So if we turn off, you will see what happens. So we turn on back, also done. So we have the fuel tank, the left and right wing fuel tank, the fuel booster pumps, the crossfeed valve, and the center tank. You can see center pumps and pressure and the balance to balance the fuel between the tanks. Automatically the fuel jettison, you dump some fuel in flight to lose weight, make the aircraft lighter. The electronic engine control for the engines and the auto start. We're gonna turn off the engine later. The wing and engine got the eyes here. You can see the cabin pressurization manual. We use the outflow valves when we climb the descent to pressurize the cabin. We use the auto, and also we have the pressurizer from the engines, and the APU also supplies the air conditioning and ventilation. So this is the main components of the overhead panel. So we're gonna make an engine start demonstration. We have also the lighting system over here and the windshield wipers. So we turn on the lighting here for the landing lights. We're gonna have better view like this for the engine start process in a couple of seconds. So really I need to show you also that the systems here. So we have the systems. You can see the hydraulics, APU, oxygen, liquid cooling. So we have the electric, you can see the left and right engine, as I told you, the ITG. You can see also the diagram here is the same one like in the overhead panel. All the systems, electric system, hydraulics, fuel system, electronic engine control for the engines, pressurization, and some other components. So you will see here all the diagrams. You can see the battery voltage, the amperage, everything is working fine. Also the APU is running, APU generator, so we can use for starting the engines. We have the left and right wing, we have the left and right engine, the hydraulic pumps, the electric C1 and C2. You can see how much hydraulic fluid you have in the tanks, the pressure 5000 psi. You can see where the hydraulic fluid goes. The fuel system you can see also, same like in the overhead panel, you can see the minimum fuel temperature below which the fuel will freeze in flight, so we use the recirculation system. You can see minus 37 degrees in flight, so we use the recirculation to the engine, controlled by the fatigue also. We have the left and right wing tank. How much fuel you have right now? 11.2 thousand pounds, and 11.2 and 12.2 in the center tank. The fuel booster pumps are all on and supply, except this one, the aft right wing. You have the low and high pressure fuel valves to the left and right engine. You can see the left and right engine, the symbol, total fuel on board. The APU is fed from the left wing using the DC motor, main DC, and also the crossfeed valve is off, but if we turn it on we can supply either engine with either tank or either pump. If we have a pump failure, for instance, or a leak, so we have overhead panel. You can see also another view of the overhead over here. So we turn on this pump, so we go back to the virtual cockpit. So we have a few more things to solve here. So this is the fuel, the air system, pressurized air from engines and from the APU, the air conditioning inside the cabin. You can see the doors of the aircraft are closed and the cabin can be pressurized. The landing gear, you can see the temperature of the brakes and the pressure of the tires of the aircraft. Flight controls, we can see this moving around the flight controls. So when we move that, you can see all flight controls react. Also the horizontal trim stabilizer, so this is how you see everything works in the wings of flight control surfaces. Horizontal trim stabilizer and rudder trim FX control panel, maintenance, circuit breakers. So we go back, I believe we have checklist like in the Boeing 777. So we see checklist components, resets, communications, some other. So this is the main thing we need to do before starting the engines. So we turn off both engines and restart them very quickly. So you can see we're gonna see both engines going off like this. You can see all the systems now coming on in yellow, in the amber color. So you can see the engines rotation is slowing down. You can see both engines are going off now. So we go over here in the overhead and reset, restart. We need to restart the engine, so we set the auto start left and right engine. So you see all the yellow, the amber lights on. So we're gonna have pressurizer inside the engines from the APU, left and right engine. You can see how much, above 21%. We can initiate, we have enough pressure inside both engines, right and left. So we can initiate the fuel flow now. So we'll let fuel flow, like this, the fuel valves on. So we have the auto start now kicking in automatically. I'm gonna have both engines on in a couple of seconds. So you can hear the sound, you can see the spinning of the engines, all the components. Also the messages, the warnings are going off because we have the engines back on again. So to start on, and we have the running engines above 62%, above 61 perhaps. So we can proceed for takeoff now. Set the flaps for takeoff. So now we can proceed for takeoff, so stay until the end part of the video. Now you can see the complete flight from takeoff, climb, cruises, and approach and landing. Some Thomas Feathers is the one breakout flying the Boeing 787-900. So I'm gonna start now. I'm gonna taxi to the runway for the takeoff and flight. So thank you very much. You can see now advance the thrust levers. You can see here. we're gonna use the tiller. We're gonna make a turn over here, align the aircraft with the runway. A little bit more thrust. So we take the runway clearance from the tower, from control tower. So we are cleared for takeoff. Only need to align here. The runway heading. Use also rudder pedals if need. So parking brakes. Just one component here. I'm gonna use after takeoff to save some frames. So we're gonna have a complete flight now. So we're gonna have also the view for the takeoff. So we advance the thrust levers forward like this. Forward position, disconnect the parking brakes and go. Full takeoff power. Engines are stabilized. So we have 70-80 knots, 100 knots. Align with the rudder pedals now using the runway alignment. V1 we rotate, and V2 we have the takeoff speed. So we hold landing gear up. So we have positive rate of climb, landing gear up like this, as you can see. So keep climbing. So we are just this. So you can see we are 2,000 feet, 2,100, 2,200, 2,400 feet above the ground, 4,000 feet above the sea level. We climb with 5,000 feet per minute. The airspeed is 200 knots, 240. So we have a good airspeed. Let's see the pitch altitude, like 15 degrees right now, the rate of climb, and you can monitor, you can see the ground below you. You can see the terrain here. You can look further away. We keep climbing. So this is the climb out from the airport right now, and the first view of the Zurich and Switzerland. So we start the turn also. Now you can see some of the terrain like this. You look the ground below you. You see. We keep climbing like this. You can see the flight plan also. So we are aligned here after takeoff. So maybe we need to retract some flaps slowly now to increase the airspeed as we climb higher. So we have 220 knots. You still see the airspeed is decreasing as we climb higher. The knots indicate, so we have higher Mach speed also. Τώρα. Άμεσα θα φύγεις. Καλά. Σε 15 λεπτά τελειώνω.
Όχι, εγώ δεν σου λέω, άμα θες μέχρι τις 11.30 να έχεις.
Καλά, εντάξει. So we keep climbing, you can see as we climb up here. All the indications are correct. Climb out, and we need 15 plus 3, 18 more minutes for this video to end. So we have a nice view flight right now. You can see that we're flying like this. So make the turn now. So we're gonna have also the nav on. You can see we balance here the aircraft in this altitude, so we level up for a while. You can see also the outside view how we are located. So this is a nicer view over here of the Switzerland. You can see the aircraft, the galaxy, the aircraft fly around us, the terrain below us, the snow-capped mountains. We have the Germany, the Bayern Munich in front of us, the Bavaria, the France on this side, and the Italy behind us, the Switzerland. Okay, gonna have also the lakes here, beautiful lakes. So we have 18 more minutes for this flight, 21,000 feet approximately. It level up for a while. You can see the flaps position. Maybe we need to decrease the flaps, increase the airspeed. So this is the lake view over here, and the France on this side. Two lakes. So we keep climbing. 31,000. So keep climbing. 0.42 Mach, and we need 17 more minutes to reach the airport. You can see keep flying like this. Darts. Thanks. So we increase the views here. You can see further away the airports, the flight plan. And the turn here we need to make in a couple of minutes. As you can see, gonna make a turn. So we need to start maybe banging here the aircraft. So this is the bang turn. Gonna make it a little bit steeper. I need to level off a little bit as we turn. So this is the turn here. As you can see, all around you the view, we have the Germany, Bayern Munich, the lakes, the France, and this Bayern Munich, Germany this side, and Switzerland. Keep turn. So we make the turn here. We complete the turn and we keep going. So we need like 10 more minutes to complete the flight, and we have the frozen vapors. As we keep climbing, you can see the chemtrails from the engines, and we have the lakes also. This is the frozen vapors, the altitude what we hold, and we have a nicer view here. So we need to stabilize the aircraft somewhere around here. So this is the altitude we need to stabilize the aircraft, and we need to start descent in a while. As you can see, this is the cruise altitude. We have to fly through here and see all the data. So we're cruising. You can see the engines here also, the indications, so the thrust levers. Let the thrust levers a little bit down. So we're gonna start descent in a while. As you can see, we have my own flight yet control the aircraft. As with level of 29,000 feet, and we're gonna fly with higher speed in a while. Like you can see the star sign, how beautiful it is over France over here, and we have this way the galaxy, the Switzerland, with Germany this way behind us, the lakes. So this is how beautiful this view is. You can see the France and the galactic view and the frozen vapors over here from the aircraft. So we need to start descending, I believe. So go back to the cockpit, and we can connect if we need the auto throttle, increase the airspeed. The autopilot. So we need descent. So we're gonna start descent. And the vertical rate descent, the autopilot connect. And now we have the autopilot connected and flying the aircraft, as you can see, and we have 9 more minutes for this flight to end. And this is again beautiful view with the autopilot connected, the lakes behind us, beautiful lakes, and the frozen vapors. Germany, Bayern Munich in this side, my homeland, Germany and the France, and this way we're going back. So we're going descend now. We need the airspeed decrease, and the altitude change. So we start descent now, the descent path here, as you can see, and we have again controls, flight controls, as you can see. It's still with the autopilot connected now. So keep descending, as you can see. Last view of the chemtrails over here. It also to extend the speed brakes. So speed brakes extend, and thrust levers to the idle. so we have 7 more minutes for this flight to end. We keep descending and following the flight path, as you can see. Having an overspeed. Full idle thrust. You can see the airspeed here. Mach 0.55 right now. We're flying with about 650 kilometers per hour. 145 knots for this altitude, 22,000 feet as we keep descending and approach to the runway. You can see the horizontal, the profile the radar scan from the terrain, and the flight plan here and here, the waypoints that we have to cross. So keep descending. We have a little bit of overspeed, but to cover 17,000 feet, descending. And we keep flying the same altitude here. We disconnect the autopilot.